And if I hit F5, will it work? No. F4? No. Maybe I don't know how to do this. Just show. Where do you see show? Slideshow.
Yeah.
No, that didn't do it.
Yeah, maybe you just click on the first slide, no?
If you click on the little icon down at the lower.
Oh, here it is. That's
left.
it.
Yeah.
Yeah, usually
Yeah,
it's
there
there.
you
A
go.
function key lets you do it, but do you have the advanced?
Yeah, I think I have the tool.
Got
Hopefully it works.
All right.
So it's a difficult task to talk about that because this subject matter, it's very huge. And what I'd like to do is really to introduce you to some of the technical issues, and we can skip some gory details, but I think it's very important to understand really basic mechanics. But I'm also interested in how this thing came about and what is that for, and what are the prospect and business issues associated with that. So it's a fairly large presentation. I'll skip some of the less interesting details, but one of the reasons, of course, as Doug said, I'm not getting paid for this. So I put it together. I spent about a week putting it all together because I did it for myself also. I want to have a proper structure for this information, that it gives me really guidance into the sea of information about this subject matter. So with that, okay. So I'm going to talk about a little bit of philosophy. What's the blockchain? What is that for? And a little bit of history of that, how it came about. And I'm going to spend a fair amount of time on mechanics of that, how that actually works. Then we're going to walk through the foundational examples called Bitcoin. And then I'll introduce you to some of the interesting applications and business considerations. And then we'll see, I'll share with you what I learned from this exercise, okay? So what we're facing today, you see this busy slide, but in our society, business and social interactions require trust. And traditionally, trust for many years was based on face-to-face interaction between individuals. And then with the advance of commerce, we needed a really better mechanism to trust each other with regard to financial and other transactions. And 1494 was an interesting year. Pisan friar, he actually buried in Pisa. His name is Luca Pacioli. He's a very interesting man. And so he published a book on double entry accounting. That's an Italian invention. So the left-hand side has a credit, the right-hand side has a debit. But he felt that the correct accounting is a moral obligation, which is appropriate for 1494. Well, how many people feel today in this room that the proper accounting is a moral obligation? You raise your hands. Well, it's a fair amount. I'm not so sure that if I ask that, I spend lots of time internationally in many different countries. I'm not so sure that I would have the same response in some other place about that. But anyway, the system is organized through centralized trust managers. That's a key observation. So we have banks, stock exchanges, Federal Reserve Bank, all these things. And they facilitate transactions through the trust. Now, many people believe that we need a new system of value exchanges. And so the trust can be organized without high cost and inefficiency of centralized systems. So so-called distributed ledger technology is really designed to do that. And besides these two entry points here, we have a third entry into something that people call immutable, undisputed, and shared ledger. I will explain what it means, immutable, undisputed, and shared ledger in a second. Now, the key issue with the trust is you can organize the trust and you can have it almost foolproof. The problem is cost, as always. The money is the problem. And so the cost of trust is an example of something that called transaction cost. The guy who came up with the first formal idea about that was a British economist, Ronald Coase. He got Nobel Prize for that in 2009. Note that it took 62 years to recognize his contribution. When I worked in Pitney Bowes, and those of you who know Pitney Bowes, so Pitney Bowes was famous for making this postage meter, become big, 35,000 people company. Well, postage meter, what postage meter does, it reduces transactional cost, no more and no less. And I actually published paper. I was the first person within Pitney Bowes, 60 years history, who recognized that and published paper about that. Now, the tool to create this new trust is called digitization. So, different forms of value. You can think about property type, music score, any kind of things that has value. And if you can create unique digital representation of that form of value, that process called tokenization. It's an ugly word, but that's the word is being used nowadays very frequently. In business literature, everybody talks about tokenization. What's the result of tokenization? It's token, right? So those are digital tokens. They represent these digital assets. What is fascinating about these digital tokens? They're actually not static objects. They can become programmable. And that opens a whole bunch of opportunities for them. So there are a couple of very fundamental issues with the whole approach. The first one is listed here. You have a physical asset, you have a digital representation. Making binding between those two is excruciatingly difficult thing. It requires great deal of ingenuity, and in many instances, it represents fundamental difficulty. The second issue is that the data that goes into this digital token, something that you tokenize, digitize, the data has to come from somewhere. And the question is where it comes from. It comes from two sources. One source is sensors. And many of you who work in inventions familiar with sensors are important aspect of our universe. So sensors can produce data that can be digitized, but the data can be faulty. The second source is humans that produce data, and they can produce maliciously incorrect data. And knowing that compensating for these two sources of errors is a very large problem. Those are the two, keep in mind, those are the two fundamental problems. The reason why I'm telling you all these things, because that's really important learning. If somebody tries to come up with the digital blockchain representation for some IT application, you have to think very carefully about sources of information and how this information gets into immutable blockchain. It can be immutable for sure, but if it contains crap, it's going to be crappy blockchain. Blockchain, as simple as that. And so now these DLT platforms, and I'll talk about the seconds of that. The idea is that they can create these three properties that would improve business application faster, cheaper, and better. Lots of hype about that. Now, a little bit of history. Now, people think that all these things frequently, that all this blockchain stuff comes from Bitcoins. Bitcoins was the first truly successful adopted application. Bitcoins, and we talk about that in details in a second. Bitcoins were invented by a mysterious person named Satoshi Nakamoto. So, the latest information I have, he was not Satoshi, it was sure not Nakamoto. His name was presumably Craig Wright. He was a cryptographer from Australia. I personally did not meet him, but I met lots of these people because I spent lots of time in cryptography in my life. And so the idea of distributed databases goes, so what I'm trying to say is this. Satoshi Nakamoto very cleverly put it all together. So he adapted different mechanisms, different concepts, and different ideas, and put it together to satisfy certain properties, which I explain a little bit later. So these are the list here on this slide. You see the list of ideas that were adapted for that. I think one of the most creative person, and I met him personally, we spent fair amount of time together, was Ralph Merkle. He was PhD student at Stanford University, and in 1979, he was totally non-traditional thinker. So he came up with, among other things, with the concept of public key cryptography, together with Diffie-Hellman, and he came up with this idea of chain blocks, a whole bunch of things. Now, the third concept, which is really that centralized chain, Interestingly, it's the guy named Stu Hauer, and I also spent a fair amount of time with him. He was a very interesting individual. He came up with those things. He was thinking about at that time when he was working at Bell Labs, actually at Bell Research. It was designed, what he designed, I'll show you the patent, for resolution of dispute concerning invention property. So it was first application for that was curiously about patents and inventions. And then these other things like proof of work, which is also Ralph Merkle. And another interesting individual was David Chaum. David Chaum was really well ahead of his time. He came up with completely, totally executable system for digital money. It didn't go anywhere. He started a company in Amsterdam. He spent years and years and gazillions of dollars he was funded. It didn't go anywhere. The reason, of course, is that the central banks and other banks and lots of other people who really have power in this world, they didn't like these ideas, and you will see why. So they didn't go anywhere. And then last thing, smart contracts. That's an interesting. The idea is due to the gentleman named Savo. This is the patent that was issued in 1992. You see, system for timestamping digital document, including whatever it is, text, video, audio, blah, blah, blah. Temporal-proof time seal establishing author's claim to temporal existence of the document. That was the concept. And that temporal existence of the document was proved by the chain of different documents that would be submitted to his company. You see, the company that first originally, so you see here, see, it was assigned to Bell Communication Research, this patent. Later, Stu and his buddy started the organized company called Surety. And the surety, the business was that if you have a proof, you want to have a proof of existence of certain document. Let's say you have a laboratory book, and in the laboratory book, you want to prove that you have this concept or idea stored. You could submit it to surety company, and they will put it in the blockchain style document, and then they hash it all together. I explain in a second what it was. And then the resulting hash of the whole chain of documents would be published in New York Times, which they actually did. As a collection of, in classified section, you see a strange collection of numbers in hexadecimal form. And that was actually the proof that this document exists. If anybody wants to dispute the existence of a document at a given point in time, they have to unravel the whole chain. And the judge can actually look at what published in New York Times and 700,000 copies or whatever was the circulation. And then from that strange block of hexadecimal numbers, he can unravel the whole thing. So that was an interesting thing that they did. Now, we did that. Now, this is the soup of terminology. There are lots of terms here. I'm going to use them, and I will try to introduce some of these things. But it's worthwhile to remember. So there we have a blockchain, state of blockchain, and DLT. I'll talk about difference between those in a second. Now, these blockchains can be permissioned, permissionless, or partially private and private blockchain. Permission means that people who have access to the blockchain are not everybody, but those people who have permission to do that. And there are certain permissionless that everybody, like Bitcoins, anybody can have an access. Now you have 4 types of participants. I explained that in a second. Then you have these cryptographic tokens and tokenization. Then you have something called digital wallet, digital trust. Consensus, distributed consensus mining, all these concepts related to interrelationship between different participants in peer-to-peer network in the context of the blockchain. Then you have different proofs, proof of work, stake, importance, proof of membership. Those are different mechanisms to prevent cheating, and I'll talk about that. Then you have transaction and smart card, and then you have different organization. And finally, these are all the traditional properties of cryptographic mechanisms. So immutability, which really means data integrity, the right, correct professional term, data integrity. Business people prefer term immutability, so we'll use that interchangeably. Irreversibility, which is really professional people who do cryptography, call it non-repudiation. Non-professional people call it irreversibility. So I sort of listed all these things for, okay. Now, the distinction is if you accept that, is that so-called DLT, digital ledger technology, is a platform. That's another popular buzzword. Everybody has a platform. Apple has a platform, and Google has a platform. And platform is something bigger than what you know, what you have. It's some huge thing. Anyway, blockchain is just element of platform. If you like that you can think about that way. And now it's a little bit more of mechanics. So now I'm going to explain how it works in somewhat details that you can see. So what is the platform? So you can imagine a collection of computers right here. So they call nodes. This collection of computers, they connected to each other through so-called peer-to-peer network. Well, Doug would know better what it is than I do. But you can think about that. So as opposed to client-server architecture, when there is a server connected like a star to all the clients nodes. Here, there are many more connections, and these computers can perform joint computation in the context of the network. So one computer can perform one part of computation, another part of computation. And they can share resources. Technically, it's organized through two layers of software. There is so-called virtual layer, which allows you to think that that's P2P. And actually, inside, there are more like traditional internet protocols. That makes sense? That
Internet protocols, I heard of them.
No, I mean how the P2P network is organized.
Sure.
So something like that. And now what is important is this classification. So what we have, each node. So now each node runs the same software as all other nodes. This software called digital wallet, in many instances, for example, in Bitcoin or Ethereum, is called digital wallet. Now each node can send and receive information directly from all other nodes. What is information depends on the application, we'll talk about that. And each node stores, maintains this shared copy of the database containing record of all agreed upon transactions application. All of that. That is the blockchain. So everybody shares the same blockchain. Now, nodes are classified in 4 categories. There are nodes that are called watcher, there are doers, full node executive, so-called, and there are core developers. I will explain a little bit later what it means and how these nodes, but that's basically classification. And the important point to remember, nodes do not trust each other. So one node can be, God knows what, on Solomon Islands, and another node can be in Ashford, Connecticut, and they don't know anything about each other except that they connected. And so if they try to transact something, there's absolutely no basis for trust. That's the idea. Okay. So the blockchain is this actually simple mechanism. So we have a head of the chain right here, and contains address and hash value of the first block. I will explain what hash value in detail is. It goes into the data, and then hash value of each block is calculated out of the whole previous block, and then goes into the data of the next block, and then goes to the next block and so on, so that they irreversibly linked. And this data can be anything. It's called payload, sometimes it's data. It could be executable script. The idea of smart contract is that inside the data is actually executable code. That is the idea. So what is the hash function? I'm going to spend a little bit time on that because it's absolutely critical mechanism to understand the whole thing. If you don't understand how hash function works, you can't understand how the blockchain works. So you have a file right here, and the file is this small text, hash function plate, blah, blah, blah. Doesn't matter what the size of the text is, there is something called hash function, and it transforms it to the fixed size numerical value, regardless of what it is. The value obviously will be different all the time. In fact, it's so different that if I change one character here, for example, I misspell word very or difficult and I put T instead of D, just one character, or even uppercase to lowercase, this value changed drastically. It will be completely different value in every single position. So the trick how you organize that it's so sensitive. Sometimes people call fingerprint, sometimes call digest, but in fact it's a hash value. it's not a new idea. The hash values were invented in the 50s because those of you who are computer science inclined, they know that searching through the database is a difficult problem. If you can store together with the value the hash values, searching through the fixed size hash value, it's a lot simpler process than searching through the whole thing. And that's how hash values were invented. But we're talking here about much more sophisticated creature. This hash value is called cryptographic hash value. So how does it work? So it's really a Swiss Army knife of cryptography. Almost everything requires hash value. Why? You can do lots of things without hash value. It will take forever, and it will be very difficult. So hash values enable efficiency in the whole system in a variety of ways, and that's why it really has such a huge application. And this function that I just showed you, this function, is very easy to compute. It's very fast. In mathematics, it's called one-way function, which means that you can compute it that way. You can take this and produce this. You cannot take this and produce this. So it's not possible. In fact, for that matter, for those of you who are curious about cryptography in general, the whole concept of public key cryptography based on the notion that there exist one-way functions with the trapdoors. And the trapdoor means that there is a secret. And with that secret, you can take this and convert it back to data. That's the whole cryptography. There's nothing more and nothing else. That's the concept. But hash values are not that kind. They really work one way. Okay. So now this is how it works for those of you who are really curious. So this is how it works. So you take any text, and it could be as large as 2 to the power 64, which is huge, anything you want. And you map it to 256-bit value. And you can efficiently compute it for all these values, and it's called hash value. Now, how that actually organized? It's a little bit more difficult than, but anyway, there is an initial value, and there's something that is the heart of the matter. It's called compression function. So compression function takes collection of bits, very large, and map it into much smaller collection of bits. That's how it works. So this can be almost anything up to the power 5. And then you break this text that you want to, or data you want to hash, into small blocks, and then you run compression function to each block and take initial value of this, and that's how it works. So that's better representation. That's how hash function is computed, or one of the mechanisms to compute that. So this is the first chunk of the text you want to hash. This is the second chunk, third chunk. You have all these chunks of the text. This is compression function. This is initial value. And then you take the first result of compression function and run the same function with the second chunk. Take the third one and run all the way down. The result is the hash value. That's how it works. And that's very, very important mechanism. And it becomes collision resistant. So what collision resistant means that if you have two different text or blocks of data, it will map into different values of hash function. And finding two different texts that map into the same hash value is almost impossible. Technically, they exist because there is no miracle in the nature, as you know. If you have huge files, and there are so many of them that you can compute, they cannot be all mapped into the fixed value without finding some that have identical things. The question is how to find these identical things. That's called collision. Okay, so, and now we're going to go to Bitcoin. So now how the Bitcoin works. So if you look at the paper money and think about what paper money do. We can take a banknote, and I give a banknote to any one of you, and you can give me a banknote, and that's a transaction. So, or I can give it to merchant for exchange of services, right? So we can examine banknotes for the purpose of counterfeiting. They have all these so-called forensic and digital security mechanism, holograms, and a whole bunch of things to prevent. Very simple. So there's no such thing as double spending because once you give up your coin or your banknote, it's gone. You cannot spend. And we have anonymity and unlinkability. Anonymity means that if I pay the cash, no one knows who I am, and I just leave, right? And unlinkability, it's hard to link what I buy and who I am to the payment itself. That's the typical mechanism of the paper money. Now, this Bitcoin, as I said, it's an electronic cash. So Bitcoin is totally decentralized. We have no bank, no central authority, but there is a committee. This committee of 5-6 developers. And when I talk about 4 different types of participants in a blockchain or in a digital ledger technology, this is the highest category. Those are the czars, the 6 or 7 or 10 people who control open source code. They are czars. They make more decisions. So there is still a level of centralization to some extent, but that's about it. So the question is how digital things can be regulated and how you prevent, how you do all these things that paper money do, and how you can be sure that the digital things, just collection of bits, cannot be double spent or triple spent. And that was the ingenuity of this gentleman, Satoshi Nakamoto, which is a Craig Wright or whoever it is. So the basic unit of Bitcoin is 1 Bitcoin. It's called 1 Bitcoin. It can be divided into any number of pieces, up to 100 million pieces. So if you want to buy a Bitcoin, it's a trivial process. You go on the web and you type in Google Bitcoin, and then it will appear this digital wallet. You download this digital wallet to your computer and you say, I want to buy 1,000 or 100 or whatever piece of Bitcoin, and you can buy it. You just do that. So they generate it at the rate of about every 1 Bitcoin and every 10 minutes, but they were kind of lowering these things all the time. So the idea is to avoid inflation. In 20 years, the total number of Bitcoins will be 21 million, and they cannot be generated anymore. These are hard-coded constants into the whole process. So why people do that? Well, it's decentralized. It's not controlled by anybody or any bank. Anyone can use it. You don't even have to have credit history. It's relatively easy to use. Transactions are irreversible and transaction fees are low. And I was watching yesterday this TV serial on Showtime called Ray Donovan. And there, a rich person was blackmailed into giving part of his company. And the blackmailer tries to cash the shares of this private company into a private marketplace and goes to appropriate broker. And the broker says it's going to be very difficult. There are these constraints, unless you want to have a Bitcoins for this share. So it gotten into the public ideas. So the Bitcoins, these are the basic parts of the Bitcoin. So there is a transaction. That's a transferring coin from one user to another. We talked about peer-to-peer network. So the blocks are a collection of transactions. So they formed about every 10 minutes, and they verified and then added to the blockchain. The mining is an interesting process. I'll talk about that in a second. But the process of verifying transactions or creating new coins is called mining. And successful miner is rewarded with the portion of the Bitcoin or Bitcoins. And the proof of work is actually, if you want to be rewarded for the work you've done, you get the Bitcoin for the work, not for selling merchandise. You have to prove the work, and that's the mechanism that is being used to prevent people from cheating. So it's a data structure, as I showed, linked list. The hash function in this case, so-called SHA-256, it has the value of the hash is 256 bit. SHA is a very good mechanism that approved by the United States government, was designed by National Institute of Standards and Technology after very careful and difficult process of selecting different candidates. But basically, this is a good candidate, SHA-256. And as far as we know, in this business, you always have to say that you make this disclaimer. Because all these ideas, as I said, all the concepts are based on beliefs. There's a faith that this SHA-256 does not have easy findable collisions, or this public key cryptography is not breakable. These are beliefs, there are no proofs. It doesn't exist. So, as far as we know, it's a very good thing. The proof of membership in this case is the proof that certain data block is really belongs to the blockchain. I'll skip that part. Those of you who know what digital signature is, it's a mechanism that essentially provides data integrity and the data origin source of authentication, just in the interest of time. These are the basic plumbing of Bitcoins. It's a 3 algorithms, only 3. One is REPEMT 160 is actually what was invented by Ron Rivest at MIT way back, and it's a hash function. It has purely service function. It just does something with the public key. It's not really that important. SHA-256 is a crucial mechanism. A digital signature mechanism, something called elliptic curve cryptography. We'll skip that as well. It's an economical way to organize public key cryptographic functions. So I'll skip that too. So what is transaction? How does it work? And then so let's say that Alice has a coin, 1 Bitcoin, and Alice obtained this Bitcoin from somewhere else, from Satoshi Nakamoto. And so the transaction that how Alice got this coin by paying at the exchange or otherwise is, oops. What did I do? Oh. Okay. So this transaction is how Alice obtained this coin. If Alice wants to pay back this Bitcoin, then we form this block. And it's actually quite simple. It's where the Alice got his coin. So we always know what money Alice used to pay back. It's part of the transaction. Then it's Alice and this block. Those are 2 identifiers. This identifier of Alice, this identifier of Bob. In practice, those are the public key. And that's the amount that Alice wants to pay Bob. And the whole thing is encrypted with this public key. And that's the whole thing. That's the transaction. And this transaction is broadcast to everybody, and transaction identified by its hash value. That's basically how it works. So here's the deal. So Alice obtained this from somewhere, this coin, TXI. It goes into this together with Alice identity, Bob identity, and the amount that's going to be transferred. Those 2 things goes to this hash function. It's mixing and mixing that, and got 256 bits. And then this gets signed by public key to protect the rest of it. That's a block. This block goes to the next one in exactly the same fashion. Now Bob wants to give it to Chris. With Bob, here is 1 Bitcoin. He got this Bitcoin, Bob got it from Alice. It's the same thing, the whole block goes here. And so that's how the whole chain is organized. And this is another representation of that chain, if you wish, with a little bit more details. It has inside. So these are the hash of the block. And it goes into the next hash, and then goes into the next hash, and that's how it's all linked together in immutable way, and has timestamp, version, nonce, target. I'll explain what it is. And the target is to whom this transaction is aimed at. So in this case, that would be Bob, and that's transaction information. Okay, so it's another representation. So transaction requested by Alice, here it is. The request transaction goes to everybody in the peer-to-peer network. So everybody gets that. Then transaction gets validated. The network of everybody gets that, and the people start working on whether this transaction should be approved. What it means approved is actually added to the blockchain as one of the links. Approval means that it's added and everybody got it. And verified transaction that goes into the blockchain, and the blockchain gets validated again, and then new block is added to these things, and transaction is complete. So that's the whole process. So it's another way of looking at this thing. So this is more detailed. So transaction owner, that's Alice, it's public key. Inputs to transaction where Alice got her Bitcoin. That's output Alice wants to pay to Bob. It goes here. And that's Bob's address, and that's the signature of Alice. That's the whole thing. So it's not that complicated, actually. People think that it's very complicated. So Satoshi generated first 50 Bitcoin. That's the head of the chain. And from there, he could pay whatever was part of that 2009, was part of that network. And he could pay out of his 50 Bitcoins, and he paid some, and then second block was formed, and then people inside paid other people, another transaction, and that's how it goes. So that's the way that it sort of went. Now, how double spend is prevented? What if Alice wants to take the same coin and pay not only Bob, but also to Chris? If Alice wants to do that, she has to generate two transactions. One is to, in this case, one is to Bob and one is to Chris. And they will have identical information as far as where Alice got the coin, input to the transaction. But it will have different address to whom that Bitcoin to be paid. And this one is to B, to Bob, another one is to C, to Chris. Now, both of these, as a candidate, goes to the network for approval. And actually, if one gets approved, another cannot get approved because it has identical information. You cannot spend it twice. So one gets rejected. And that's the mechanism of rejection. It's a clever mechanism that Satoshi Nakamoto invented to prevent all these things. Now, let me talk a little bit about that proof of work. So in order to create this block and add to the chain, you have to prove that you actually work on that, because the people who do this kind of work, they call miners. Those are the executives in the chain. And executive has terms of the nodes, and they have to spend a lot of computing power doing that. And so in order to do that, what this cryptographic puzzle or a proof of work was invented. How does it work? Is the hash of the previous block. This is something that you can think of that as a counter of transactions. So each time transaction happens, or the block is a candidate for inclusion, a new of these things is generated. And then there are all candidate transactions here. And you go through a process of hashing that to create a candidate block to add to the blockchain. What was artificially introduced in this case is the notion that the block that is going to win, anybody can do this. This part can be done by anybody. Anybody can SHA that and get it. But what is required, that the SHA value, the value of the hash function, will have number of leading zeros in the hash value. And it turns out from computational perspective, as far as we know, there is no better way to compute that by just exhaustive search. So in other words, you run this transformation on your computer, and you get lots of garbage. You run this transformation, and you find something that has zero. You store that, say, has zero. Now you run this again until you find second zero, and then you run again and again and again. And you have to search all possible combinations. Another way to think about that, because the way the hash function is organized, as I showed you, it functions a little bit like a random choice. The hash value of a given block is almost like a random choice. You can predict that. And because it's random, there is no structure in there. And in order to find the right structure to this data, which is number of leading zeros, you have to go through exhaustive search. And yes, I skipped that, these forks in the blockchain. That's a mechanism. Sometimes it happens that the two blocks are competing. And basically the way it's organized, the longer part of the chain gets accepted. And that mining finding these zeros, finding this mining is excruciatingly difficult process because it's exhaustive search. You basically have to run these things. It's run by specialized hardware. You cannot run that. So you can see here on this slide, a PC can do 2 to the power 23 hashes per second. That's how PC does. You have to do 2 to the power 63. It's an enormously bigger number than this one. And so PC will take 25,000 years to generate a block, single PC. That's why it's a specialized hardware. And that's why it's such a huge problem for Bitcoins. Because last year, the generation of Bitcoin every day, functioning of the Bitcoin blockchain required as much electricity as the whole country of Switzerland. So the entire consumption of highly developed economic industrial country of Switzerland consume per day the same amount of electricity as a Bitcoin mining. Okay, so that's mining. So users will accept the block all transactions are valid, obviously, as I said. Hash previous blockchain is a public ledger, that's fine. So, what's the properties of this? It's readable by anyone, because if you want to buy this Bitcoin, as I said, you go to Google, you download on your computer so-called digital wallet. This digital wallet will do all these things for you. It can read these things and can verify things, and you can create the candidate blocks if you want to engage in transactions. Well, the value of Bitcoins has a huge fluctuation. So it went from 25 cents, somebody bought pizza in 2010, to 20,000, almost $20,000, that's $7,000. So it's all speculative. I'm going to skip security notes. It's actually interesting consideration. So people think that it's all anonymous. It's not quite all anonymous, because all transactions are stored in a publicly available database. And so law enforcement agencies can and do examine blockchains every day. And they're looking for patterns. If you pay with these blockchains, whom you pay and how you do that. And it's actually, there's a mechanism to visualize the entire blockchain, the entire ledger on the computer. And you can see through computer graphics activities. It's like a dashboard. You can see exactly what's going on. So it's not entirely I already talked about that. Now, in niche application, you probably know that extortionists love Bitcoin. So also called ransomware attacks frequently use Bitcoin, just like in my example with the TV Ray Donovan. The Bitcoins are, because perceived anonymous property with these things. Okay, let me skip that. So those are the 4 basic challenges with that. Now, scaling Bitcoin is a very difficult thing. It turns out that because of the hard-coded severe limitation, only 7 transactions per minute are possible. And increasing that to larger number of transactions is difficult. Because the blocks that added to the blockchain have to be verified, it has high latency. Then people can use fake block generation to even increase latency. And finally, the energy consumption I already talked about. Now, this young gentleman is a Russian immigrant by the name Vitalik Buterin. He's from Canada, Toronto, and he was a student of my friend. And he invented this in 2013. He was 19 years old. He invented the alternative mechanism for Bitcoin called Ethereum. Now, the key distinction between Ethereum and Bitcoin is that in the payload, he introduced a smart contract. So in Ethereum, you can actually execute code inside the blockchain, while in the Bitcoins, it's just a transaction data. And so they formed alliance in 2000, and there are a whole bunch of companies, Microsoft, all the big names, Credit Suisse, they all, it's being perceived and being promoted as a platform. So Ethereum is a platform, EEA. Now, let me switch to applications. So what are the applications? Energy, internet, food, agriculture, manufacturing, real estate, medicine, elections, all these things are. I'm going to walk you to a couple of those things, but those are potential applications. There are tons of companies now that are trying to jump on the bandwagon, and I will show you sort of the hype around that. But that's basically different types of applications that people thought of. One other way to think about that is in terms of how many users, billions, 100,000, millions, or thousands, and so for totally permissionless, and everybody can participate, currency payment mechanism is a clear mechanism. People do it for crowdfunding also. And then you have hundreds of thousands or thousands for decentralized autonomous organizations, these kind of things. Now, this is another slide, actually borrowed from one of the Alan's presentation. So here it is. This is financial application. It's banks, financial services, and insurance. So you can see the market, and this is in millions. So $70 billion are projected to be 2024. The bulk of those things still will be financial applications. The healthcare and supply chain, Internet of Things, are three other applications are perceived to be promising for that. So now examples. Insurance. How you do that in insurance? So if you want to insure something in property and casualty business, is an asset that you have. So if you can identify the asset and do this, what they call tokenization, as I explained, create digital representation of those things, you can verify the ownership of those things by putting ownership through the blockchain mechanism, and that's basically the idea. So it may be useful for insurance. I spent a little bit more time on that because, in my opinion, I'll show you a little bit later. In my opinion, this is kind of more promising application. I have a slide here in this presentation to the real success stories, what really happens up to date, and where people enjoy real success. And so we have three issues in supply chain: counterfeit, visibility, traceability, and efficiency. Efficiency, it's obvious, it's this faster, better, or cheaper. But traceability, feasibility has other aspects associated with that in supply chain. I'll walk you through the food supply chain, but in food supply chain, if the problems arises, or I don't know, what they call it, coronavirus and God knows what, you want to know where it comes from. And traceability allows you, it's an audit trail. That's the property of that. And so that's one way to look at that. I took it from Gartner, so you can find it on Gartner, but I'll try to explain what it is. So here's this Internet of Things platform. So this Internet of Things platform, you can think about, you can see it because of, sorry. So you can think of that as a sensory data. You can have temperature, you can have speed, you can have other things that are attached to your shipments. And that forms metadata, something that goes into the blockchain. Now here is what they call artificial intelligence managed beef distribution. So they have all sources of beefs and the transportation units and the warehouses and all these things. So the blockchain attempts to obtain data from the farmer as the first time the animal was actually produced, to the processor who kills the animal and does other terrible things to it, to distributor, and then retailer, customer, and regulator is included. Those are the entities that are involved in those things. Each entity contributes to the blockchain. Each entity adds something to the transaction or smart contract that goes into each block. And then the whole block is visible to everybody. The claim is that, well, you see, this is Gartner. I'm a poor English speaker, but I would know that the word to use here is improved trust, not increased trust. Increased implies something quantitative. And the same thing is here. So they're not really doing that. But anyway, so it's improved in trust and quality, improved trust and provenance where it comes from, and then it's the smart contract goes into those things. And then you can sort of see the restaurant, all these things that stored in this can be viewed by anybody. And I'll tell you practical application result of these things. Now IBM. So IBM is huge in this supply of chain DLT, digital ledger technology, or blockchain. So IBM claimed to create this platform. Why IBM is doing that? So I was talking to all on the way here. So IBM missed two revolutions. First time when Microsoft and client-server architecture came about, and IBM lost it to Microsoft and was out. And the second time when Google and search engine and all the internet and the World Wide Web came about, they missed it again. Now, IBM believed that this is going to be the third revolution. This is going to be the most important technology of the next 15, 20 years. And they don't want to miss that. So they're putting huge amount of money and creating these things. They really are lots of people in IBM working all over the world to make them the leader for anybody. And that means that you can join their platform, you can use their software, you can do all these things with IBM. That's what IBM does. So that's another example. So IBM is big in the supply chain. You can do that, the same blockchain for voting application. You can have sort of created the distributed blockchain with the shareholder vote, chairman who approves the shareholder votes, and auditor put it all in the blockchain the way that healthcare, it's another application. So basically what we were talking about is creating a blockchain that contains clinical data. So when you have a laboratory technician that enters the data, I don't know, it's X-ray or MRI or your blood analysis or whatever it is, it makes sure that it creates the block, and then the block goes to all potential providers that would need to share this data. So in this case, of course, this would be an example of permissioned blockchain, because only people who have permission to access this data will have access to this data. The advantage, of course, it's data integrity protected. So once it's there, no one can change this data. So one possible application, you have a lawsuit because of some malpractice, and people may change clinical data because they want to protect themselves. That would protect against this kind of applications. An interesting, curious application in cats. So people created this game of CryptoKitties, and you play this game, and the result is some sort of CryptoKitties that they can proliferate, they multiply, they do all these things. In 2008, one of the kitties was sold for $140,000. Now, the beautiful thing is that kitties are traded only within closed blockchain market. And in this case, it's a curious example if you think about that. The kitty is a digital file. It's a collection of zeros and ones. But yet, it cannot be reproduced, because the mechanism of reproduction is protected the same way as in Bitcoin double spend. Once you have this kitty, you own that. No one else has that. So it's an example of totally digital data that cannot be reproduced without really violating all sorts of things. That's an art application. Now, well, and this is, I'm going to skip that tokenization, and I'm just going to.
I just wanted to ask, could you allocate some time for questions? Because
Sure.
I think some people will have questions.
I'll just show you a couple of things. So, and it's another 5 seconds. So, top 15 technologies. The blockchain, according to some people, it's number 3 on the list. These are, somebody said, those are the things that are going to be big things in the next 20 years. And I'm going to skip all these, and I just, real success stories. That's all. So IBM Food Trust, just one example on the top. Tracing given product in normal supply chain was 7 days. IBM claimed that they reduced it to 2.2 seconds in supply chains. And there's other examples of this application. I'll skip that. So what I learned, so I'll share with you what I learned. So this DLT is a clever tool, there's no question about that. You have to carefully choose the application and on well understood criteria. But it's not panacea, it's not going to work equally well, and some application has huge limitations that's almost impossible to overcome. You have to look at what I call controllable characteristics of these things. Controllable characteristics of this size and access. How many entities we're going to have access to the network, and what's the size of the networks. What kind of allowed smart contracts and management of input data. Those are the issues, and they must be defined vigilantly. regulatory issue is a huge impediment. So, for example, those of you who are familiar with what GDPR is, it's a European regulation controlling privacy of data. It comes into huge conflict with the way that the blockchain or DLT problem works. And supply chain seems to be, at the moment, a killer application. I'll stop here. Sorry, I ran a little longer than.
No, it's fine, you can talk more, I just thought we
Is
would
the
not
stick
like
on
to
the-
allocate a little time for the.
Is
Well,
this
if you want to have some
We're
other.
recording the whole thing, and can we upload your deck to the web, is that okay?
Well, because I borrowed freely from all sorts of sources, I would avoid doing that. Now, if you want to give it privately to somebody, well, because I didn't create this data. You see, I didn't have time or desire to work on these things, create all these beautiful things. I just found what I need and I put it into the system and I borrowed. And so lots of things, not my creation. I presented you with my understanding of these things, both from technical and business perspective. So
So the answer is no.
Or could you make it available by email?
Yeah, by email, I guess. It's okay.
yeah, by email it's okay. But putting on a website means somebody find your website and say,
Sure.
wait a minute, it's mine. No one asked my permission to
Sure,
put
I hear
it
you.
there.
That's
And
fine.
I don't want to deal with these issues. So
That's
it's
fine.
not immutable. Okay, so if you want, there are some other examples of where it's going in terms of business. There are a whole bunch of slides there, but I guess you won't have time for.
Some questions, I
Yes.
guess.
A question, what % of your own money have you put into Bitcoin?
0.
Okay.
I'm not a gambler. So actually gambling is a huge application. A lots of applications. Gambling and gaming and extortionist, those are huge applications for traditional cryptocurrency.
Yeah, what concerns me when I